Okay, so we're up to topic 3 in the modules 8 to 10 section. So where this is in the textbook, let me change the sharing here. Okay, so in the textbook, it's this unit 4 on probability. Because modules 8 through 12 are all related to probability. I sort of break that up into 2 parts, the part before random variables and then after. So I treat like 8 to 10 as sort of a thing, and then 11 and 12 is a thing. So this is where it is in the table of contents of the OLI textbook. Now, in our Canvas modules, we're here at the beginning of Module 8, Probability, and we have these mini lectures and materials, and actually on the schedule, the idea was that you would view these on Friday, so now it's Monday, but we had the one on probability axiom models and axioms. Okay, so that actually we kind of got through that last week. Okay, let me back up here. And then we come to the 9 and 10 part of it. Okay, and we come to the logic of events. And so that is the homework that's due tonight. And these videos, these are the ones I was talking about. These videos were ideally we would have watched those on around Friday or so to get started with the homework. So they cover the law of the complement, law of unions, mutually exclusive events, conditional probability, all the rules of probability. And then what this homework does is you pick the right rule to solve a given problem. And so those are kind of outlined and summarized in the workbook, but the workbook does not give you the detailed explanations. Those are in the videos and also in the textbook. So looking over here at the workbook, it's just a summary stating each of the rules of probability. But then explanations with pictures and examples, counting events, this sort of thing, those are in the videos. Okay, so this one's going to pick up, what I'm planning to do today with this session is to go through the homework on these. And so, if you're going to be watching this at home, I would urge you to go back and watch those other videos first, or this might not totally make sense. Okay, but here's our story. The probability it will snow is 0.3. Okay, so the idea is as we repeat this experiment, let's just think of it as you wait for the next day and you see, did it snow? And so you can do that repeatedly. And the idea is this is predicting in the long run, if you go on forever, it snows 30% of the time. Then the second sentence, given that it will snow, the probability is 40% that the plane will take off on time. So this is saying if you only look at the days when it snowed, then 40% of them, the plane takes off on time. And given that it does not snow, if we only look at the days when it did not snow, 70% of those, the plane does take off on time. So that's the given information. We set up our notation. We let S be the event that it snows. Let T be the event that the plane takes off on time. So when I say the event that it snows, what do I mean? I mean the list of all the outcomes in which it snows. Now, where people have trouble, it's figuring out, like what is the sample space, what is an outcome, what's the set of all the outcomes, and so forth. Visualizing that jargon is a little bit of a problem. So what I want to do is fill that in a little bit. Just right over here on the paper. So in this story, what's the experiment? So we look at a randomly selected day. And so we're picking days. You look at a day. The outcome of selecting the day, it's the day that you got. Now this is tricky. It's like if you had a big population of people and you were randomly selecting people. And the outcome, okay, it's the person that I got. Okay. So now the population, it's the set of all days. So there's this event S, the event that it snows. So it's a subset of the population. It's just the set of days when it snows. And so event T is the set of days when the plane is on time. So when I talk about P of S, the probability that it will snow, I mean, this function P, it's a model. So you have to start with a model. Okay. Now, you don't always have to use an equal likelihoods model. Okay. So it could get to be real fancy. Maybe not all the days are equally likely, or some days it's more likely to snow than other days. Okay. We don't need to know what the model is to work the problem. Well, however it's being computed, we just come out that the probability of this event is 0.3. So if I was using an equally likelihoods outcomes model, an ELO model, just to make it easier to visualize, I could show you, okay, in that case, here's where the 0.3, the 30% would be coming from. Okay. I just have my sample space, or population, or sample space, I should say. Set of all possible outcomes. If that's you, then what I could do in an equally likelihoods outcomes model is just count the days when it snows and divide by the total number of days, and so that would be my probability. That's where the 30% would come from. Okay. By the way, Nikita, are you able to see this okay on your screen? I should have checked earlier.
Yeah, I am.
Okay. So when it says P of S, and I fill in the blank, I just put in the 30%. So what's the probability it does not snow? It's 100% minus the 30%, or 70%, 0.7. Now this symbol here, the probability that the plane's on time given that it snows. So back in the story, well, that was also 0.7. That's a little confusing. There's two 0.7s in the problem, but they don't have anything to do with each other. Okay. Anyway, let's see. So it says, given that it snows, the probability is 0.4 that the plane will take off on time. Okay, so I'll put my, well, that one was given. And it was given to be 40%. Okay, and what does that thing mean? It's among just the snowy days, what percent of them do we expect the plane to be on time? I'm sticking with just counting the outcomes here, equally likely outcomes. It's not necessary that would be our model. Okay. But it makes it easier to picture. If it was that way, then what you'd do is you'd count the snowy on-time days. So we're looking at just among the snowy days, what percent of them is the plane on time? So you look at the snowy on-time days, divide by the number of snowy days, because we're only looking at snowy days. And so that's what this bar is about. This is given, and there's more detail in the videos prior to this one. Okay. So that one was given in the story. And same way here, this one was the other 70%. There's two 70% in the story. That was given. And now we come to our first one. So we need to find the probability that it'll be snowy and on time. That's out of all the days. What percentage of those is it snowy and on time? And so we go back to our list of probability rules. And we scroll down to the one on intersections. Probability that A and B both happen. It's probability of A given B times P of B. So let's apply that over here. So we get 12%. Now, what is that saying? 30% of all the days it'll snow, and 40% of those days when it did snow, the plane's also on time. So it's 40% of 30% of all the days. That's 12%. So we can fill that in over here. I need to write down the formula that I used. So I'm using P of T given S, P of S. Is 12%. Yeah, editing and in the PDF reader, the Adobe Reader, it's hard to get the symbols. So instead of using the little bar here, I'll just say not. You could print it and write it on paper or take a picture if you wanted to. Okay. So what's that? It's, let me write it out over here. So the T given not S was 0.7. P of S was, P of not S. Not S goes here. That was 70%. So in past semesters, you know, when we meet in the classroom and I kind of walk around and help students with this, Now they get down to here mostly pretty good, and then get stuck on, okay, so now what's the probability that the plane's on time? Now, first, let's just think about it in sort of a practical sense, and then I'll go back and we'll see where it comes from in the formulas. Okay, but in a practical sense, 12% of the days it's on time and snowy. 49% of the days it's on time and not snowy. Are there any more days when it's on time besides the ones when it's snowy and the ones when it's not snowy? Well, no. There's just the snowy on times day and the not snowy on times day, and that's all the on times days there are. So I need to add these two things together. So I do P of t and s plus P of t and not s. And I kind of need to edit the workbook to give more space here because I had forgotten that when you get into Acrobat Reader, it's no longer easy to get the symbols. So anyhow, we'll add those together, the 12 and the 49, and we get what, 51, 61. Okay. And so it goes. I mean, if you want the probability that something does not happen, it's 1 minus the probability that it does, you know? So it's whatever left is left over from that 61%. Now on the P of t, how's that coming out of the general rules? So that's this law of total probability. Now I've got a bunch of pictures about that in the prior videos. Okay, but I'll just illustrate it, you know, in this one, in this video, what I'll do is I'll just illustrate it for this one homework problem, but it's an application of the more general rule from the other video. So, I mean, what it is in this situation, so here's your sample space. So that's the set of all the days. And then in the general formula over here, we have this exhaustive set of mutually exclusive events. What's that? So I have this set of events. So each event is a set of outcomes. Okay. So we got B1 in this story would be like some set of days, some event. The B2 would be some set of days, so forth. A bunch of events. They're exhaustive. What that means is that they cover all the days. They cover all the outcomes. That their union has a probability of 100%. There's zero probability of something happening that's not in one of these. That's exhaustive. And then mutually exclusive events, meaning they don't overlap. There's zero probability that you would have an outcome, a day that's both in B1 and B2. So they cover the whole sample space completely without overlap. Now, so in this story, what are those? Well, you have the set of snowy days and the set of not snowy days. That could be your B1 and your B2. So these are your snowy days and your not snowy days. I mean, why make up new letters? And no need to make up new letters. I'm just doing it to show how it relates to the general statement of the law of total probability. So you've divided the sample space up into two parts. And then we're trying to find what's the probability that the plane's on time. So in your general statement over here, you're trying to find the probability of an event A. So in this story, that would be, you're trying to find the probability that the plane's on time. So it's T from our story. And all this law of total probability says is that you add up P of A is the probability of snowy N on time, P of A intersects B1, it's saying you add these two parts together. And so that's what we did. We did probability of on time and snowy plus the probability of on time and not snowy. And so the general statement is just, well, it's not just like, it works not just when you have a problem like snowy and not snowy, but you could break up the sample space here into, 3 or 4 different parts any way you want to. And then you can just add up the little probabilities from the overlaps. So you can just add those two together. It's this part plus this part. Okay. Then the union over here, I'm going to skip the not, you just do 1 minus. Okay. 1 minus P of T. I won't skip it. Okay, 39. And for the union, we've got our law of unions. So you just plug in probability is snowy or on time. You do the snowy plus the on time and then subtract the part that they have in common. There's a good explanation of that in the previous video, so I won't redo it, but you just write down what's the formula I'm going to use. writing or instead of the union symbol because it's hard to get the symbols here. So you do that arithmetic and you get whatever you get. Not that, the probability of not anything is 1 minus that thing, so that's easy. And there's just these last two. And that goes back to De Morgan's laws. So I think I need to give you a picture for De Morgan's laws now. Okay. So there's a video on De Morgan's laws. But not a write-up in the workbook. Okay. So the complement. If you're not in A union B, so the union's the whole MasterCard symbol. The complement is everything outside. These guys outside. If you're out there, you're not in A. You're also not in B. You're in what not A has in common with not B. If you're not A or B, then you're not A and you're not B. So that's De Morgan's laws, one of them. And the other one is if you're not in the little football, if you're not in A and B, not in the intersection, that means, well, if either you're either outside of A or you're outside of B. You got to be outside of one of them. So that's this. So how do I apply that over here in this problem? Say this is the same as that. So if I can work out this one, I already know that one. The not S and not T is the same as not S or T. So whatever I get in the previous line, I've got it here. So let's see. P of S plus P of T was 30% plus 61%. So that's 91% minus that should be an and. Minus 12%. So 91 minus 12 is what, 79. And this is 1 minus the 79, so that's what, 81. I hope I'm doing the arithmetic right here. I don't know, S plus T, 91 minus 12. Yeah, I guess that's right. Oh, 1 minus 79. I'm sorry, that's what? 21. Okay. Well, and then because of De Morgan's law, these are the same thing. How about this one? Use the other De Morgan's law and something that you've already got. Okay. So not A or not B. It's the same as not A and B. If I want probability of not S and T, I do 1 minus probability of S and T. Well, that's 1 minus the 12%. It's 88%. And homework 2 is the same kind of thing. I'll leave that totally to you, but notice the given information is different. This time, in the first example, you're given the P of T given S and the P of T given S, not S. Given that it snows, given that it does not snow. Okay, but in this other problem, your information is probability of rains and cancels, not rains given cancels, rain and cancels. So it's different. But the strategy is the same. You just go back to your list of the probability laws and you pick the one that you need and you go from there. So I'm going to go ahead and stop this recording.